So welcome back, everybody. And the topic today, as you can see from the notes, is to try to finalize this electron gas calculation. And then we are going to move into another extremely popular mean field method, which is called density functional theory. And that's the kind of state of the art if you're dealing with material science, for instance, or if you want to study large systems like molecules or molecules in the DNA or whatever. So if you're doing bioscience simulations where you need to dive a little bit deeper than the cell level and do the kind of microphysics, then density functional theory is one of the more favorite methods. And we are going to lay out the basic framework, but then we are not going beyond that because there is actually an own course at the University of Oslo which deals only with density functional theory and its applications. So we have always to be a little bit careful so we don't create too much overlap. And also the focus here is beyond Hartree-Fock methods. So that means FCI, for instance, which we have discussed, but also many-body perturbation theory, copper cluster theory, Green's functional theory, and other many-body methods, which would typically use a mean field as a way to embed the environment and have a better starting point for dealing with correlations. So on Friday, I thought of using perhaps only the first lecture on density functional theory, and then we're going to use the rest of the time to discuss the midterm, and then work on the midterm, if that's okay. And if people prefer, we could tune down the lecture on Friday as well and just reserve Friday for midterm discussions. That's very much up to you guys. So what I want to do now is just quickly remind you of what we did last week. And then after all these kind of gory treatments of these integrals, we are going to reach the holy grail, which is the calculation of the expectation value of the interaction and the Hamiltonian. We did the kinetic energy last time, and now we are going to see that the final expectation value of the Hamiltonian is going to be something which is proportional to the density of the system. So the reason why we do this long journey, just to reach this final tiny goal, is that the local density approximation serves as an input to density functional theory and the way you treat correlations. And that was something which was introduced back in the 60s and is still nowadays one of the standard approaches here. So let me just see here in case there are some more problems here with the sound. So it's a little bit hard to hear today. Okay, so let me see if I can increase that one. And also, let's look at audio settings. No, that should be okay. So let me, just for you online, can you still hear me?
Yes, I can.
Okay, so I think I just needed to take away some of the options which I had here. Now, what I want to do now is to just quickly remind you of some of the things which we did last Friday, so that we bring back some of the technicalities, and in order to be able to fulfill the calculations here. So what we have assumed, and you can actually show that, this is something which we just stated without a proof, is that the Hartree-Fock single particle wave functions are actually given by plane waves, which again are given as a solution of the kinetic energy operator. And this is something you would get for a particle in a box with infinite walls. We have the spin degrees of freedom, which we're going to bring back. And this leads to the standard periodic boundary condition, which you probably saw when you took one of the basic courses in quantum physics. Then the total Hamiltonian contains the kinetic energy operator in second quantization. And then we have the operators here. And if we express the Hamiltonian in terms of the second quantized operators, if we add the spin degrees of freedom, this is the typical matrix element or integral, which is a better wording for it, where we sum over the spin degrees of freedom and then the wave numbers, which are quantized. But at the end, when we are going to evaluate these integrals, we are going to take the thermodynamical limit, where we are going to make the density of these wave momenta denser and denser, so that the sums change over to an integral. Now, the integral here, on the other hand, as we went through last time, is then given by us simply plugging in the plane waves, is then given by these two terms on the bra side, and then the similar terms on the ket side. And then when we plug this in, and this is what we did last time when we looked at the integrals, we're also going to expect that the integral exists over V of R. And that led to a conservation law. So we have the Kronecker deltas for the spins, but also if we recognize this integral over one of these quantities as a delta function, then the whole integral reduces then to this integral which you see here. And this is something which we evaluated last time, so that when we set up the integral and use these conservation laws, we could then rewrite this term, which you see here, in terms of an integral which is finite, which can be integrated up, and gives us a very simple result. And then we have a sum over these momenta here. I'm going to bring this up in the whiteboard again. Then what we also did was to compute the expectation value with a given Slater determinant. In our case, this could be the Hartree-Fock Slater determinant. And in that case, what we did was simply to evaluate these terms here. And we found that this is given by the Fermi momentum to the power of 5. There's a volume element divided by the mass, and then a natural constant. And then we also calculated the density of states. So we have the number of particles, which is something which we can also calculate. And we went through the calculation last time. So this is just a repeat of the results which we got. And we could then rewrite the Fermi momentum in terms of the density. So you see now that the Fermi momentum is, as expected, something which goes like density to the power of 1/3. So the density of the system is the number of particles divided by the volume. And that means that we could then rewrite the expectation value of the kinetic energy as a function which has some natural constants times the density to the power of 2/3. Now, what is common then, since n, when you take the thermodynamical limit, this is a quantity which obviously diverges because you're looking at an infinite amount of particles, you calculate the expectation value of the kinetic energy and also the potential energy per particle. So that means that we divide by n, and then we have something which depends on your constant, which we assume, on density, which we assume to be constant. So that is the expression for the kinetic energy. What we are going to do now is to calculate the expression for this quantity here. So let's go through these final details. And this is roughly going to keep us busy this lecture and parts of the next one. Let's try to do that and switch to the whiteboard. So what we are going to calculate now is the expectation value of this quantity here. So we have the operator in second quantization. Let's just quickly remind of what we did last time. So we're going to write this V as an operator in terms of second quantized operators. There's going to be a sum over spin 1 and spin 2. So in the original case, we had a sum over 4 spins. But then due to the Kronecker deltas, we could reduce that one to a double sum. And then we have a summation over these wave numbers, which we loosely normally always call momenta. So I'm writing these as vectors because in our case, we would typically have a 3-dimensional momentum. So there is an X component, a Y component, and a Z component. And then we have the charge squared, the volume times a factor of 2.5. And then we also got a factor of 4 pi. And then we had this cheating factor or this convergence factor, which we are going to let go to 0. when we have performed the final calculations. And then we got plus this q squared. So let me remind you of what these different terms are. This is then multiplied with an A of sigma 1, dagger. And then we had a conservation of momentum, which we have to obey. And I'm going to bring back what these definitions stand for. So let me just write down the expression. So these are the subscripts for the creation and annihilation operator, the states they refer to. So we have a sigma 2 of K, and then we have an A of sigma 1 of P. So one of the things which we did last time was to show that the incoming momenta and the outgoing momenta have to be the same. So we have any momentum conservation. And when we set up a typical Feynman diagram for this process, what we had then is an outgoing momentum K1. This had a sigma 1. We have an outgoing momentum K2 here, and a sigma 2 here. And then we have a K3 and a sigma 3. And then we have a K4 and sigma 4. Now, what we did last time was then to introduce some new variables. So we have that K1 plus K2 is equal to K3 plus K4. We can manipulate these expressions and introduce the relative momentum. So what we would do then is to define new variable. So this variable Q, let's just write it down here, is then given by K2 minus K4. So we would typically write this momentum here as a K here, now Q here. And then we would also have that K1 is equal to K3 minus Q. So we have the same, if you look at the relation which we have here, if we now just switch over K4 to this side, so we have K2 minus K4, and then we switch K1 over here, we have K3 minus K1, and that has to be equal to Q. Then you see immediately that K1 is equal to K3 minus Q, okay? So these are just some manipulations of an introduction of new variables. Then we are going to introduce a new variable just to simplify things. And this is K3, which we simply call for P. So that's the P in the formula, which you see there. And then we also define a new variable for K4, which we simply call for K. And this is just to simplify the notation a little bit. So let's us frame that one in here. And that means obviously that the K2 is then equal to K minus Q. And K1 is obviously equal to P plus Q. So with these definitions, we can then also redefine K1 and K2. So let's do that. So what we will have then is that K1 becomes then equal to P plus Q. And K2 then is equal to K minus Q here. So what we had then originally, when we looked at the original expression, if we go back then we had 1/2. And in the original expression, we had a sigma 1, sigma 2, sigma 3, sigma 4. And then we had a K1, and we had a summation over K1, K2, K3, and K4. That was the original term. And then we had a K sigma 1, K2, sigma 2 here. And then we had the interaction, and then we had a K3, sigma 3. And then we have a K4, so we're just writing out in all gory details the quantum numbers. And then we had the creation of and annihilation operators of K1, sigma 1, of A, K2, sigma 2, dagger, A, K4, sigma 4, and then A, K3, sigma 3. Now, one of the things which we found last time is then that the Kronecker deltas for the spins, we have the orthogonality relations, which means that sigma 1 have to be equal to sigma 3, So if we go back to the original image, which you see here, this was where we started. So we had a K1, sigma 1 coming out, K3, sigma 3 coming in, and the same on the right-hand side here. So originally, what we did was to start with this expression. Then, when we looked at the integral here, we could actually find a simplification for that integral by calculating it. That gave us two Kronecker deltas, which simply said that sigma 1 has to be equal to sigma 3, sigma 2 equal to sigma 4. And then we got that K1 plus K2 has to be equal to K3 plus K4 from the interaction itself. And that means that this general expression, which you see here, can then be written out when we calculate this integral. We have inserted the Coulomb interaction. When we did that, we can reduce this to a double sum instead of quadruple sum. And then this is a triple sum instead of a quadruple sum. And then we have these constraints, and we have simply rewritten the variables like that. So this is just a rewrite of the variables in terms of something which looks a little bit more compact. But now you see that the K1, for instance, which is equal to P plus Q here, is something which you then would have, sorry, this was actually missing K1 here, sorry for that. So this term here is something which we had here, K1, but then is translated into this term which you see here. And then K2 is given by K minus Q, and you see that one here. And then we simply have replaced K4 with the K and K3 with P here, like that. Okay? So let's try to calculate something with it now. So the kind of interaction elements which we have now is something which we can rewrite. So let's just do that. And let's rewrite the sum. So we are going to rewrite the sums now in terms of one sum. So we are going to rewrite the sum over the momenta P, Q, and K in terms of two terms. One, where we simply sum over P and K and put Q equal to 0. Plus, so there's nothing which hinders us from doing that, right? So this is just a rewrite of the sum. And then we have P, K, and then Q different from 0. So if I single out this term with 0, then what you will see then, if we do that, is obviously that in the term with 0, then Q equal to 0 here will simply give 4 pi divided by mu squared. Okay? And then we have the other term, which has Q different from 0. And there's a reason why we're going to do that, because this integral, when we have mu squared here, without Q, with Q equal to 0, is something which is going to give us a simple term when we calculate expectation values. Okay? So let's look at the first term, the one with Q equal to 0. So let's just write that one down. And in that particular case, what we are going to get is something which looks like this. So we have E squared, we have 4 pi, we have 2 divided by omega and mu squared. And then we are putting in P and K. So we put Q equal to 0. And then we have sigma 1 and sigma 2 here. And then we are going to have, so the matrix element is pretty simple, or the interaction term. And then we have an A sigma 1 dagger. And then we have P plus Q. And Q is equal to 0, remember that. So this is put equal to 0, so we don't need to deal with that one. And then I have an A sigma 2 here, and then I have K. So originally I had minus Q, so let's just put in minus Q, but just keep in mind that that one is equal to 0. And this is multiplied by A of sigma 2 here of K, and then I have an A of sigma 1 of P. So now we're going to calculate the expectation value. So when we calculate the expectation value, the only thing we need to look at now, so if we now just leave out this constant in front of it, what we do then is that we are going to calculate the expectation value of this quantity here. We have the Hartree-Fock ground state. There is a sum over P and K and sigma 1, sigma 2 here. And then we are simply going to calculate this expectation value here of P. And then I have an A sigma 2 here. And then I have K. And then A sigma 2 of K and A sigma 1 of P of phi 0 Hartree-Fock. Now, in this particular case, we have not normalized the operators to the vacuum state, the new vacuum state. So we can now set up the contractions which will be present. So we are going to have two types of contractions here. So let's just write them down. So we're going to have a sigma 1 of P dagger, A sigma 2 of K, of A sigma 2 of K here, A sigma 1 of P. So the type of contractions which we can have is obviously this one. Then sigma 2 is equal to sigma 2. So that means that, and we also have this one, sigma 1 is equal to sigma 1 and P is equal to P. But then we can have another contraction here because we know that we can also do that one. Then we are forcing sigma 1 to be equal to sigma 2. That's a fully possible state. And then we are forcing P to be equal to K. That means that for the first term, this one, that gives us a simple Kronecker delta. So we just get the Kronecker deltas for sigma 1s with sigma 1. But then I will have a double sum over P and K. And then I have a double sum over sigma 1 and sigma 2. So these two double sums, if you then look at the expressions which we had earlier, so if I just set up this one, P of summation of P of sigma, and these are states which now sum up to the Fermi level, that summation there is just equal to the number of particles because we are summing up over all the states. So if you think of all the states up to the Fermi level here, so you could have a P1 and then you have a sigma 1, you have a P2, sigma 2, etc., up to a P of n of sigma of n, like that. And that means that one of these sums gives us a number of particles. So in this particular case, the first term keeps the double sum. So that gives us a number of particles squared. The other term obviously reduces because then we get a Kronecker delta here where we have delta sigma 1, sigma 2, and then we have a delta of P and K. That comes with a minus sign. So that means that this reduces just to a single sum, a sum like this one. So then I'm just getting the number of particles. So when I bring everything together, what happens then is that the expectation value of the Q equals 0 term, that gives me now a pretty simple expression, which is E squared or pi. And then I have a factor of 2, the volume element, times this factor mu squared, and then n squared minus n. Now, there's something which I didn't go through in full details in the calculations, and that is that there is a similar term which I get from the interactions of the electrons with the background, and a term which comes from the background ions. They will come with opposite signs, and they will cancel these two terms in the limit where mu goes to 0. So if you go into the Jupyter notebook, you will see the terms which come from the electron background. So let me just bring that up here. So let's just go back to the notes from this week. So when you now look at these terms, if we just scroll down a little bit, there's going to be an interaction part, and that term which we have seen now is going to cancel this term from the positive background. So this is just the density of protons or ions which we have. And then this is an electron background term. And these two terms, one of them is going to go like n squared divided by v, and the other one is actually going to go like n, it's actually n divided by d. So these two terms are going to cancel the term which we have from the q equals 0 term in the thermodynamical limit. So what remains to be done then is actually to calculate the term where we have q different from 0. So what we need to look at is the second term, which is this one. And this term is given by sigma 1, sigma 2, and then I have a sum over p and k. And then I have q different from 0. There's going to be a constant with the electric charge, the volume, factor of 2, or pi of mu squared plus q squared. And then when we've done the with calculation, we're going to let the mu go to 0. So this is a typical calculation trick where you put in a convergence factor. And then you do the calculations, and then you hope that this gives you something which is finite when the term goes to 0. But then what we are going to have now is an A sigma 1, and then I have P plus Q dagger, and then I have an A sigma 2 of K minus Q dagger, and then there is an A of sigma 2 K, and A of sigma 1 of P. So now we are going to look at the different term, because in principle, when we now look at these kind of interactions here, the way you should think of this is that we are having a direct term and an exchange term. So if you now look at the this type of calculations in more general terms, so what we are going to set up now is this phi 0 arc, and then we are going to look at A sigma 1 of P plus Q, and then dagger, and then we're going to have an A sigma 2 of K minus Q here, and then we have an A sigma 2 of K, and A sigma 1 of P, and then phi 0 of repok. So I'm skipping the summations. So when we now look at this, we have again two possible sets of contractions which we can have. So the possible set of contractions is obviously this one. And now keep in mind now that Q is different from 0. And then we have the other one, which is this one. Okay. And then we can have the next contraction where we take these two guys. Now, if you look at the first contraction, this is going to require that delta K minus Q is equal to K, and Q is different from 0. So this is not possible, right? So this has to be 0, because K minus Q is not the same as K. And secondly, we also have a times a delta of P plus Q with P. And you see again that this is also not possible. The spin parts are pretty easy. So we will have a sigma 1 with a sigma 1, obviously. And then we have a delta sigma 2 with sigma 2. But these two parts here, which you see, this one and that one, they clearly are not possible because Q is different from 0. So they have to be different. So this is 0. So the only term which then can give us something, hopefully, which is different from 0, so this will be this term here. If we now look at this one, what we are going to get in that case is that delta P plus Q is then equal to K. And then I have the next one, which is delta of K minus Q here, equal to, in that specific case, equal to P. And if you now look at these two expressions, this actually matches. So K is equal to P plus Q. If I look at the next one, this is also the case. And then I have a delta of sigma 1, sigma 2 here. And in that specific case, it means that the double sum over the spins reduces just to a single sum. Okay? Does that make sense? So if I bring everything together now, so what I will have is simply now that K minus Q is equal to P, And obviously, the other one gives me P plus Q is equal to K. Okay, so if I do that now, I can reduce the summation to just a summation over one of the spins. So it's a spin up and spin down. The interaction which we have, this guy here is spin independent. So when I now reduce this one just to a single sum, that means that I'm summing over the spins. So that gives me a factor of 2, because this guy here is spin independent. So I get a factor of 2. There is also minus sign because I have to interchange the positions of the creation and annihilation operators in order to perform the contractions. So what I get then is that the expectation value, which we are left with for the Hartree-Fock term, for the interaction piece, now has two terms which are cancelled by the electron background and the background contribution. And then we are only left with this final term here, which is minus 2. And I'm going to single this one out. This is due to the spin degeneracy. So I have two spins, spin up and spin down. The interaction doesn't depend on spin. So I'm just having two terms. Then I'm getting 2 pi e squared divided by the volume element. And then I have a summation over P of K. And then I have K different from P, obviously. They have to be different because in the equations which we had here, we said that Q is different from 0. So K cannot be equal to Q. No, so K cannot be equal to P. Sorry. And then I'm going to get a term which goes like 1 divided by P minus Q squared. And this is actually the term Q squared, which we had before. And we have taken the limit. We have taken the limit. Lim mu goes to 0. So the original expression has actually this term which you see here, mu squared here. We have the Q here, which is P minus K. Now they can never be 0, so Q can never be 0. So that means I can safely take the limit of mu going to 0. So then I'm having a term here now, which is simply due to the exchange part of the interaction. So we have a term, only the exchange term, and this is a correlation to first order interaction due to the Coulomb interaction and the Pauli principle. Only exchange term. So you may say now that, hey, isn't this guy going to stop now? Aren't we happy? You can actually calculate this one now because you see here we have a summation of a P and K. This is a summation which we will now translate into the thermodynamical limit. So we are going to change these summations over all the states below the Fermi level, and we are going to make the difference between each momentum smaller and smaller. So this is going to translate into an integral. And when we calculate that integral, this is actually an integral which we can evaluate analytically. And this is the final exercise, which we are going to do here, okay? So we need another few minutes where we go through the final detail. And then we reach the so-called Holy Grail, which I promised you. And you will be extremely excited when you see the final result. So sometimes it's okay to see all these kind of small details, which we are going to go through. So the thing which we are going to change now is actually the summation over K and P. So this applies to P as well. So this changes into 1 over 2 pi cubed. And then we have an integral over K. And since we are in 3 dimensions, this is a 3-dimensional integral. And we do the same with the P. In the expressions now, I'm going to leave out the fact that P cannot be equal to Q, but I'm going to bring that back when we are going to solve the integrals, okay? So then what happens if I include this, if you look at what we have here, then this term here, since we have only one volume element, we need to multiply with a volume here and a volume here in order to perform this transformation for both K and P. So what we are going to get then is minus 4 pi E squared, we need another volume element. And then since we have two summations, this is 2 pi to the power of 6. And as I said, I'm going to bring back the problem with the fact that P and K cannot be equal. So just wait a small moment. And this is then multiplied with 1 over P minus K, and this is squared. And the fact that it's squared is something which will allow us to perform the calculations analytically. So let's rewrite this integral, and let's now only single out this piece here. So let's take that part. So that part is going to be given by 0 up to Kf. I have a d3p. I have 0 up to Kf. And then I have a d3k. And I'm going just to write it out in terms of the squared values. So when you don't see a vector, that means that this is just the absolute value, k times p times a cosine theta here. Then I'm going to change this one into a variable mu here. Not mu, but u. Sorry, the letter u. Sorry. Okay. So let's take a closer look then. And we are going to define a new variable, which I'm going to call s, which I call for k divided by p. That means that I can rewrite this integral as a d3. I'm skipping the limits, plain laziness here, p squared. And then I can rewrite it like 1 plus s squared minus 2 of s times u. And now we have to look at cases where p is obviously different from k. So we can have a case then where p is larger than k. That's one possibility. And then we will have another case where p is less than k, but they cannot be the same. That means obviously that s is smaller than 1 in that specific case. Now there is a very important formula which you may have seen. This is one of these generating formula. So you may have seen this one, 1 plus s squared minus 2 times s times u. This is given in terms of a partial wave expansion. We have L, you have s to the power of L, and then you have a Legendre polynomial, which takes u as an argument. Have you seen this expression before? So if you've gone through, let's say, a course in mathematical physics, and you study solution of differential equations, this is actually what's called the generating formula of the Legendre polynomials. So this P of L is a Legendre polynomial. And I guess that you've seen Legendre polynomials before, right? So this is one of these formulas. So that means that if I square it, I simply need to square the right-hand side. So if I square this equation here, this is minus 2s of u, that simply becomes a double sum. And then I put this as a lambda, and then I have s plus lambda, and then I will have a pl with argument u, and p lambda with argument u. So what I'm going to do now is just to plug in these terms into the integrals. And then there is a nice property of these guys here, the Legendre polynomials, that these guys actually, they form a set of orthogonal polynomials. So I can use the orthogonality properties of Legendre polynomial when I'm going to evaluate this integral. So what I'm going to do now is simply to take this term, which I have here, and plug these guys in. And then there will be one term when p is larger than k, and one term where p is smaller than k. That's the way I will take into account the fact that p and k cannot be the same. So I will have two contributions, but they are going to be symmetric, and they're going to give the same result. So when I'm setting up things then, what I will have to evaluate, one, there are two terms. I'm just writing up the first one, and the other one is exactly the same. So I will have a dp, and then I will have p less than kf. That's one of the integrals. And then I will have an integral here with k is less than p. That's a constraint on k. And then I'm going to have a dk, k squared. And then obviously I get a 2 pi from one of the angles. But then I have, since I'm using, instead of sine theta, cosine theta, which goes from 0 to pi, I'm then changing variables. So I get an integration limit from -1 to +1. And then I have this du. And this is multiplied with the double sum of L and lambda. I have K divided by P. I'm just setting in the terms here. L lambda. And then I have 1 over P squared. And then I have a P of L of U and P of lambda of U. And there is another term here where I'm now having an integral. So I'm just writing it like this and with dots, P less than K. And then I have an integral from K less than equal than Kf. And the terms look pretty similar. So the expressions are going to be the same. So they will give exactly the same answers because P and K are just integration variables. They are dummy variables, so I can relabel them. And you will see that that gives the same answer. Now there's a very important property here. Legendre polynomials, and I love Legendre polynomials. I don't know how many times I have used them. Countless number of times. They have an orthogonality property, which simply says that we have a 2 of L plus 1, and then d lambda L. So now I can actually use the orthogonality properties of Legendre polynomials when I'm looking at this term here. So that obviously limits one of the sums to L or lambda. And then I will have L plus L, so I will have 2L. I have P squared here. I have another K squared here. So that's going to give me 2 times L plus 2. Because I have a K squared here, I have a P squared here. So that integral, if we now just look at that integral, one of these, what I'm going to get then is the following. So if we just write the first integral, and the other one is going to be exactly equal to the same. So the first integral gives me 4 pi. I have an integral over d3p. I have p less than kf. And I have k less than p of dk. And then I have L, and then kp. And then I get, as I said, 2L plus 2 here, because I had 1 over p squared. I take out the angle, now the k, which has a k squared. So that gives me the other factor of the k to the power of 2. And this is then multiplied with a sum which goes like 2 over L plus 1. Okay, so this specific sum which you see here, this one, with this guy here, has an analytical expression which you can look up in tables over summation, over sums. So you can actually show then that this is equal to 8 times pi squared. And when I integrate up over k, this reduces down to an integral over d3 of p times p here. And then there is a summation over 1 over 2L plus 1 multiplied with 2L plus 3. And these sums are independent of the variable p. So this becomes equal to 8 times pi squared. And then I have a kf to the power of 4. And then I have a sum. So I'm getting actually 2 terms now. So this is the term here. The original one should actually give 4 pi. But then I have a factor of 2 from the other integral. That gives exactly the same answer from the other int. So that's why I'm setting up, I should actually put an arrow here. This is 8 pi squared. And the expression now, so one of the pi's here comes from the integration over the angles, because here I will also have an integration of the angles. and that is going to give me a factor of 4 pi. But then when I integrate here over p, I have p times p squared. So that gives me p cubed, and that gives me a factor of 1 over 4, which then cancels another factor of 1 over 4, which I got from the angles here, which was a 4 pi. But then I have a 1 over 4, which comes from this integral here. So if I do that, then what I'm going to get is the total expression is going to be given by 1 over 2L plus 1 over 2L plus 3, like that. Now, this sum is something which you can also evaluate. So let me do that before we take a break, okay? So this is the expression which we get when we are only looking at the integrals. I've taken out the other constants, which we will bring in after the break. But if you look at that sum, which you have here, this sum over L, and this is the final step before we take a break. If I write this out, I can actually write this out by changing the variables. So I can write this out as 1/2, and then you have a sum over L, and it's 1 over 2L plus 1 minus 1 over 2L plus 3. Okay? So you see that immediately if I just multiply up, I get a 2L plus 3 minus a 2L plus 1. I get a factor of 2, but then I have a factor of 1/2 here, and then I'm back to 1 here. Okay? So you have 2L plus 3 here. No, sorry, not that one. You get 2L plus 3 minus 2L plus 1. That gives a factor of 2, which is then taken away by that one. Then you can rewrite this one as 1/2. I just single out that one. And then I have plus 1/2 times L equals 0 to infinity. So I just rewrite the sum here. If I pick the first term, I get 1/2. But then I have an L plus 1, which I then relabel the sums. And what I get then is simply 1 divided by 2L plus 3 minus 1 over 2L plus 3. And that is the famous number 0. So this gives us 1/2. That's a nice way to calculate that integral. Don't you agree? I feel quite some excitement about these things. I hope I can convey the excitement. It's not always that exciting to see the solution of integrals, but these are cases which we can solve. And the thing is that in many cases, we will encounter, for many of you who will do many body physics, you will often encounter the Coulomb interaction. And this is one of the cases where we can set up an analytical expression. So that means that the final term is actually, when we look at the final term, let me just set that one up, and then we are going to rewrite it a little bit after the break. So when I collect everything, this is going to be equal to minus E squared times this volume element, Fermi momentum to the power of 4, divided by 4 pi cubed. After the break, we're going to bring back kinetic energy, and then we will have a final expression for the expectation value of the Hartree-Fock energy for the system. So it's actually one of the few cases where we can get an analytical expression for both the Hartree-Fock energies and the ground state energy of the system with one Slater determinant. When we bring in correlations, life becomes not that easy. And actually, the electron gas is still much debated when it comes to many body physics. It sounds a very trivial system, simple system, but there is still a lot to do. And there are papers every year about people coming up with new approaches to the electron gas. But for us, this last term is actually an entry point to density functional theory. which we will start discussing after the break. Okay, so let's take a break, okay? Okay, so before the break, we came to the equation for the interaction energy with a Hartree-Fock basis. This would be the same interaction energy you would also get if you didn't assume a Hartree-Fock basis, because the single particle wave function is given by a plane wave. And that single particle wave function does not change when you go into an interacting system. However, what changes is the Hartree-Fock single particle energy due to the interaction. So if we now look at this expression which we had, we can now bring together what we had from the kinetic energy and manipulate it a little bit in terms of the density of the system. Because this is one of the things which is going to make us depart from what we have done till now, and when we move into density functional theory. Because till now, the energy has been a functional of a wave function, which in our case is, for instance, the Hartree-Fock wave function, a Slater determinant in this specific case. But then we're going to replace the expression with a functional of the density. And that has some pretty unique properties, which makes density functional theory actually a very, very interesting theory. And Korn and Hohenberg did actually get the Nobel Prize in chemistry for that. I think it was back in 98, I think it was 98, yeah, something like that. But let's now just rewrite this equation here. So one of the terms which we defined was the density. Just change color. So we have a density which we have labeled as n, which is simply the number of particles divided by the volume of the system. And then we defined also this radius of a sphere, which the electron, which defines the area which the volume which an electron occupies. And we defined last week this volume. We call this an RS. So this letter which you see here is my desperate attempt to write the letter R. Okay. It's actually one of the letters I've been struggling with since I was a small kid, and it hasn't changed. So when I was in first elementary class, I just had to sit over and just rewrite R again and again and again, and still I haven't succeeded. Something 60 years later. Yeah. I hope you can forgive me for that. So this is simply just the inverse of this quantity here, and it's 1 over n. Then we can calculate Rs. This is given by 3 divided by 4 pi times n to the power of 1/3. And then what we also have is that the Fermi momentum cubed is given by 3 pi squared times n. So these were quantities which we derived last week. I'm just reminding you of them now. And that means that I can now rewrite this energy which you see here, this one, in terms of the Fermi momentum and the density. So let's do that, because then we get an expression for this term, this phi 0. So remember now that what I'm writing here is not fully exact, because I've taken out the terms which cancel the electron background and the background term. So this is just a result after we have subtracted those terms from the full Hamiltonian. But what we get now is this expression which we rewrite like an E squared times the volume of 4 pi cubed. And this is given by 3 pi squared of n divided by the volume. And this is to the power of 4/3. And we can then rewrite this term here. Now, when we look at these different constants and we just plug in their values, and we introduce a 1 Rydberg, which is 13.6 electrons. So we can rewrite then the total expectation value of the Hamiltonian when we now add the kinetic energy. So let's just bring that back. And then we are going to plug in values here. So because this term, which you see here, this term here, when I now plug in 3 pi squared to the power of 4/3, divide by 4 pi to the power of 3, and plug in the numbers, this is actually the same as, and I'm dividing with the number of particles, like that. So this is the same as 2.21, and then this is divided with the radius, an electron of a sphere which an electron occupies, the volume an electron occupies, divided by the Bohr radius squared. This is a typical way you would see this expression in the literature. The constants in front of the expression here become 0.916. And then I take E squared and break in H cubed and have the mass, etc. And then I can rewrite everything in terms of the radius of an electron, not the radius of an electron, but the radius of the volume of a sphere, which an electron occupies, divided by A0. And this is multiplied with 1 Rydberg. And 1 Rydberg is a standard unit which you will often encounter in atomic physics, molecular physics, and condensed matter physics. And I just wanted to remind you that this ratio RS over the Bohr radius is typically something between 2 to 6 in metals. So if you now look at the expression again, if you look at the interaction term, you can actually see that this is something which we can write in terms of a density. So if you look at this term here, this is nothing but the density of the system. So if we now take the expression for the interaction and divide by the number of particles, so if we look at this term, so the interaction term divided by the number of particles, because remember now that the volume, when you take the thermodynamical limit, that goes to infinity. But the ratio between the number of particles, which also goes to infinity, and the volume stays constant, and that defines the density of the system. So the interaction term is something which we now can write. So divided, and I write it like this, divided by the number of particles, is E squared divided by 4 pi cubed. And then I have a volume term, and then I divide by the number of particles, and then I have a 3 pi squared of n of omega of 4/3. So depending on how you want to deal with it, if you don't divide it by the number of particles, you will see that there is a density dependence, which goes like 4 to the power of 3. If you divide it by the number of particles, this is something which you then obviously, because this term which you see here is nothing but 1 over n here. So that means that what you would get then, when you put everything together, is that this becomes E cubed, and then I'm putting out this term 3 divided by 4 pi squared, and then I have a 3 times E, no, not that one, sorry, it shouldn't be a 4 pi cubed, it should not be that. And then I have a 3 pi squared to the power of 1/3, and then I have the density to the power of 1/3. Because the term which you have here is just 1 over density. And then you have density here to the power of 4/3, so that gives you density to the power of 1/3. And this lays the foundation for density functional theory. So what you can say then is that this term is actually equal to minus a constant times the density to the power of 1/3. Now, depending on how you look at things, if you look at the finite volume, you can then think of this as something which runs like density to the power of 4/3. And this forms the basis, and we are coming back to that, forms the basis for the local density approximation, or the LDA, or the local density approximation. And then we need to derive the local density approximation. And this is something which we will do most likely tomorrow. So the local density approximation, this is called LDA in density functional theory. Which we will just call DFT. Now that was a long, long excursion, which took us 4 lectures, roughly, to get to that result. And normally you would just see this one being stated in the literature that this is the local density approximation, then you wonder where does it come from. So hopefully we can fill in some gaps here and there. But now we are moving into density functional theory, okay? So that's our next topic, or DFT. So the question now is, what do we have now? What have we seen till now? So let's remind ourselves briefly about Hjorth-Jensen theory, what that actually is and where we started. So before we jump into density functional theory, we are going to look at a reminder here of Hjorth-Jensen theory. So what we have done is to assume that the energy is a functional of an ansatz for the wave function. Is a functional of, and I'm putting this into parentheses, an ansatz. Ideally, you would like to have the exact wave function, but as an ansatz is a functional of a wave function, or just a state function, since we are looking at time-independent theories till now. And in our case, this has been a Slater determinant. That's the ansatz which we have started from. In our case, a Slater determinant, which is an approximation to the ground state, and we just label this as a phi 0. So that means that the energy, E Hjorth-Jensen, is actually now a functional, and we write this with this square parenthesis. This is an ansatz of, is a functional of this ansatz. And we also know that this trial wave function changes to a trial wave function phi 0 plus some delta. And then we optimize this term. And by optimizing that one, we get the Hjorth-Jensen equations. And what we actually did when we looked at everything in second quantization, so this serves also as a kind of a reminder of what Hjorth-Jensen theory is and what are the basic assumptions. So in second quantization, this is just the product of all equation operators acting on the true vacuum state. And the I is a state below the Fermi level. And this means also that when we now look at the variation which we had, so this variation, and this is what we used also to calculate the stability conditions for the Hjorth-Jensen equations. This is given by a sum over the particle states and the hole states. And then we have simply a one particle, one hole excitation. So where we vary these coefficients, and then we have an AI acting on the vacuum state, the reference vacuum state. This is equivalent to what we did when we changed the single particle wave functions. If you remember what we did in the beginning, so we have a state below the Fermi level, which then is changed into a small variation where we mix in a state above the Fermi level with the same symmetries. So this is equivalent actually to that term. And if we use the first one, this term here, then we get the Hjorth-Jensen equations where we vary the coefficients. Alternatively, we can vary the shape of this function, and that gives us the Hjorth-Jensen equations as a coupled set of integral differential equations, which leads to slightly more complicated equations to solve numerically than us simply getting these coefficients from an eigenvalue problem. And then what this led to for us in practice was a set of equations where we looked at the one particle, one hole block and the transition elements from the ground state to that block, which simply becomes equal to 0. So this is a practical equation which we ended up solving. And we would typically get that if we then vary this energy, if we take the use variational calculus and simply vary this part of the wave function. And we require that one to be 0. This also led, from a practical point of view, to a set of single particle equations where we now have an operator F, and where we require that this one is equal to 0. And that was the same as our H0 term. And then we had A plus what we call the Hartree-Fock potential. And the Hartree-Fock potential is simply given by this sum of the states below the Fermi level, and it modifies the motion of a single particle state due to the presence of all the other particles below the Fermi level. And this is given by AJ, anti-symmetrized. And this operator F is the operator which we also call the Hartree-Fock Hamiltonian. And this Hartree-Fock Hamiltonian, when that acts on one of these single particle states, P, that gives us simply epsilon P Hartree-Fock. So these are the eigenvalues of the Hartree-Fock Hamiltonian. Okay, so this is basically the starting point which we used in order to derive the Hartree-Fock equations. So we started with this small variation which we have up here, and through that one we then could derive these equations which correspond to the same as us finding a similarity transformation which transforms away this block of matrix elements in the full Hamiltonian matrix of many-body states. Okay? Now, what is density functional theory then? So density functional theory is actually a variation of the energy as a function of the density. So we are assuming now that there is a functional of the density which we can use to find the ground state of a system. But this promises actually much more, because with the ground state of the system, we can also recover all other states with some label. So DFT is now something which we are going to define as a function of the density. So energy is a functional density. Functional of density. And that means that the type of equations which we are going to look at now, if we look at this from a variational calculus point of view, this is going to be the same as us varying the density instead of varying the single particle wave, the wave function of the system. You see now, the basics is variational calculus, which is also the same we used when we did full configuration interaction theory. But now, instead of varying the ansatz for the ground state, we are going to vary the density. And there are actually some fundamental theorems which follow from this, which gives a much more fundamental approach to many-body physics with density functional theory. However, at the end, in order to solve the equations, we have to take a practical stand. And the practical stand is called the Kohn-Sham equations. So there are two essential theorems plus a corollary, which actually give fundamental statements about the energy as a function of density. But then clearly, any such fundamental theorems have to be applied in practice. And when we apply them in practice, we have to find approximations. And the approximations are actually the Kohn-Sham energies. And these Kohn-Sham equations, and these Kohn-Sham equations are equations which are Hartree-Fock lookalikes. But the simplest approximation is what's called the local density approximation. And that's where the electron gas comes back again. So there is a kind of hierarchy here. We are going to look at two fundamental theorems. These two fundamental theorems about a many-body system as a functional of the density, allow us actually to say that if such a density exists, there is a unique state which describes the system. Then the practical implementation is obviously, because if we could find this exact density, then we would have solved all problems. And there's no need for you guys to be here. Okay, so what we are going to look at now are some definitions, and I'm going to skip back to the slides. And then tomorrow we are going to go through the derivation of the Kohn-Sham equations, and we are going to look in more detail at some of the theorems. So now I just wanted to give you a bird's view on density functional theory first. Okay, so let's try to do that. I'm going to stop here and then share the, so we're going to go dive into the slides a little bit. And these should be, no, not that one. I have to find, where did I put that one? Not here. No, okay, let me just bring back, I just wanted to bring back the PDF file, not the Jupyter Notebook, because the Jupyter Notebook sometimes is more difficult to read. So let me just bring that one up here. Sorry for this intermezzo here. Okay, now we should be able to share it. So we are going to use the slides for the rest of the lecture. And this part begins a little bit later. So let's just go through, because this contains many of the basic things which we went through previously. So it was actually back in the 60s, 64, Hornberg and Kohn proved that the total energy of a system, including that of the many-body effects of electrons, exchange and correlation, in the presence of a static external potential, that could be the potential which is set up by an atomic nucleus, is a unique functional of the charge density. So the charge density is actually the density of particles multiplied with the fundamental charge. This is also a quantity which you can extract from experiments. And the minimum value of the total energy functional is the ground state energy of the system. And this electronic charge density, which yields the minimum, is then the exact single particle ground state energy. So the electronic energy is said to be a functional of the electronic density, in the sense that for a given density here, there is a single corresponding energy. And there are two theorems, which we will elaborate a little bit more about tomorrow, in connection also with the derivation of the Kohn-Sham equations. We will probably also, as I said, tomorrow, we will also spend parts of the lecture on the first midterm. So we will probably just have one lecture on DFT, and then we will conclude the DFT discussions next week. So this is actually a theory. If you go to fields like material science, studies of systems with thousands of interacting particles, it's kind of the basic kitchen item when you are trying to find a first approximation to the ground state of a system. And Walter Kohn, who actually got the Nobel Prize in chemistry, developed also what's called the Kohn-Sham equations. And these Kohn-Sham equations are the practical implementations of the theorems from density functional theory. And it's widely used in quantum chemistry, material science, condensed matter physics, and also in low energy nuclear physics. And basically what we are going to do now is to, you would typically start with the Schrödinger equation, which we have been discussing again and again. And just to quickly remind you, we'd have kinetic energy plus some potential energy term. And this potential energy term is the one which sets up the interaction between the electrons and the atomic nucleus, which we have. And let's just skip some of these things. This is basically the Hamiltonian which we are going to look at, where we have some external potential, and then we have the electron-electron interaction. So you can replace the explicit Coulomb repulsion with a more generic two-body interaction, which will be this term here. And actually here there should be, I see there is a small typo here because it should actually be multiplied with the wave function. Let me just take a note of that one. So actually here there should be a parenthesis and another parenthesis multiplied with psi of r, and then you have the energy. Sorry for that. I didn't see it before now, actually. So the external potential is, as we have seen before, is something which in atomic physics and molecular physics is normally given by the charged ions, which you have. So you would have an ion at a position rj, and then you have this electron ri, which then sees the charge which is set up by the background. And if you just have one single atom, like neon, atomic neon, or any of the standard atoms which you're familiar with, then you would just have the position for the atomic nucleus. And normally what you expect in these approximations is that the atomic nucleus, which is much, much heavier than the electrons, is something you can think of an object which is fixed. So that's one of the standard approximations which are made. Actually, there's a lot of research in quantum chemistry nowadays where people try to improve upon that by adding the system which also includes the atomic nucleus and the interactions between the atomic nuclei. But the bulk of the motion of the electron is dictated by an external field which is set up by the atomic nucleus, plus the electron-electron interaction. Now, there's something which we did discuss in the very, very beginning of the semester, and that is something which we defined as a density operator. When we did this in second quantization, that simply reduced to a dagger A, and that counted the number of particles. So this density operator is just given by these Kronecker deltas. And then when we are calculating the expectation values here, this is the expectation value of this operator. And when we integrate this over all of space, that gives us the number of particles in the system. So this is something which we are going to go through in more detail tomorrow. Now I just wanted to bring in the basic quantities which we are interested in. So just keep in mind that we defined in second quantization the number operator, which then simply evaluates how many particles are present in a state. And the number operator in second quantization is a sum over the individual single particle states we have. And then we have an A dagger, a creation operator and an annihilation operator. And if you go back a little bit in time, you may remember that we calculated the expectation value of the number operator, and we found that that is equal to the number of particles. So this quantity which you see here, and we are coming back, but let me just go back to the whiteboard because we are going to discuss that in a little bit more detail tomorrow. But I just wanted to bring it up here. So the number operator, which we have seen, so let me just remind you of these quantities. In second quantization, we define this as an operator n, which then simply runs over all the states which we have available. And then, so I'm just putting I here because this can be states above or below the Fermi level. And it contains AI of AI here. So in principle, we should actually write P here because this can be a state above or below the Fermi level. And then when we calculated the expectation value of the ground state for the number operator, like this, and this is one of the exercises we did some time ago, this is then simply equal to the number of particles. So the sum of the P's runs from the first single particle state to, in principle, infinity, but this just picks out the number of particles which are present. Does that ring a bell, what we did way back? Now, if you look at the same operator in what we loosely have called first quantization or in coordinate space, then what we have is an operator n of r, which is simply given by the sum over all the particles which are present. And then we have a Kronecker delta of r minus r prime here. Sorry, ri. No, it's not a P prime actually. This is just something which was left over. So it's not a P prime. Sorry. And this is actually going to be a sum over Ri here. Then you can calculate the expectation value. So when I don't put the hats on it, so here is a hat on it. When I don't put the hats on it, these are the expectation values. Then, and we are coming back to this tomorrow in more detail. Now I'm just stating the equations. This is now given by the expectation value between a given state psi, this is a money body state. We have the operator and psi divided by the norm, of psi here. And when we now perform the integral all of space, then we are going to get n of r equal to the number of particles. So one of the other quantities which we will see tomorrow, in case we have a Slater determinant with a Slater determinant for the ground state. So I promise that we are going to go in more detail through them tomorrow, because then we need to look at the properties of these operators with a Slater determinant, which is then given as a product of given single particle states. Then this operator, this n of r here, is actually going to be equal to the sum over the states up to the Fermi level. So if we have a Slater determinant phi 0, so this is then a Slater determinant which is defined by all the states below the Fermi level. This is going to be given by phi, these are the single particle states of r squared. So we are coming back to these equations here. And then if I integrate this up over all of space, this is going to give me the number of particles. Okay, so that was one of the elements which we will look a little bit in more detail tomorrow. But let's now go back to the other parts of the theory which we are going to develop. So here this psi can be any state. What we assume is that it has been normalized properly in many of the equations. So this is the quantity which we are going to look at. We did actually derive this in the beginning of the semester, but we are going to remind ourselves tomorrow about how we got it, okay? So we assume now that you find a solution for the Hamiltonian, and where we have used this Born-Oppenheimer approximation, which means that we have taken out the interaction between the atomic nuclei. So that means that we have only electronic degrees of freedom. That's a Born-Oppenheimer approximation. And we found a ground state, and then we have a certain electron density, n of r. And then the strength of the Coulomb interaction and the mass of an electron are constants of nature. So the only input that can possibly influence the electronic density and the energy of a ground state is the choice of external potential. So what we are going to assume now is that the mass of the electron is a fundamental constant. We have the Coulomb interaction, which contains the electric charges and other fundamental constants. So that means that the only thing which can change this one is now actually the external potential. So that means that the ground state energy is a functional also of the input potential. So this is a very important aspect when we are going to look at the Hohenberg-Kohn theorems. And there are two theorems plus a corollary, as I mentioned. A functional, as we have said before, is nothing else than a function whose input is another function. If you think back of what we said about Hartree-Fock, the function is the wave function, which we have used as an ansatz. But in the case, the functional takes as input the electric potential generated by the ions and outputs the ground state energy. At first, this result seems a little bit counterintuitive. After all, the ground state energy clearly contains the kinetic energy, the interaction energy, and the potential energy. And only the latter term explicitly depends on the potential. Then you can actually write the ground state energy in terms of a separate functional for the kinetic and interaction energy and the potential energy. And knowing this functional for any given potential V of r, then you minimize the right-hand side by checking all possible electron density distributions. So the problem is that we don't know this functional, and even if we did, we don't know how to find the right electronic density. So this sounds like a kind of tautology where we're just biting ourselves in our tail. So the unknown functional should describe this kinetic energy and interaction energy of a system described by, for example, this Born-Oppenheimer approximation. And even though you cannot find its exact shape, you can look at its shape in some limiting cases that we can solve. And for the electron gas, we know that the homogeneous electron gas has a ground state energy which runs like this, which then corresponds only to the kinetic energy. And for a slowly varying electronic density, you can approximate this kinetic energy to the full potential, full functional as the energy evaluated at each point separately. We are coming back in more detail to this tomorrow. And you can also then derive the simplest energy contribution from the Coulomb interaction, where you would have the density. This is the wave function square. And these are also quantities which we will discuss in more detail tomorrow. So I'm just setting up some of the basic assumptions here. So that means that we are going to get a Hohenberg-Kohn functional, which then includes kinetic energy, an integral over this external energy. There is this term here, which we will recognize as the Hartree term. That's why it stands Hartree here. And then there is an exchange correlation part. And often you have an expression for this external potential, which could be the electron acting with an atomic nucleus. The Hartree term is something which we can calculate if somebody gives us the density. But then the exchange part is something which is unknown. And that is where the local density approximation kicks in. So tomorrow, what we are going to do is actually to look into more detail into these equations, because now what I want to do was to give you a kind of bird's view on the type of Hamiltonian which we're going to look at. And this Hamiltonian will depend on the densities. But I haven't explained to you why the Hartree term can be written as a function of density, why this term can be written as a function of density. So now I just took the liberty of throwing equations at you. And then tomorrow we're just going to see how the density comes in to these expressions. So this is the starting point for the Hohenberg-Kohn functional. But then we need actually to look at how do we arrive at these different terms. And then if you scroll down here a little bit, we are going to derive the so-called Kohn-Sham equations, but we're also going to look at the Hohenberg-Kohn theorems. So this will be partly tomorrow. And I thought that we could take the first lecture on density functional theory and go through some of these basic equations here. How do we arrive at these? What do they mean? And then next week, we will then most likely derive the Hohenberg-Kohn theorems and discuss also the Kohn-Sham equations. After that, we are going to start with another many-body theory, which is many-body perturbation theory, which is also something which has been used for many, many decades. And then we can, towards the end, we can decide whether we want to do copper cluster theory or Green's function theory. We will probably not get the time to do both of them. Okay, I just wanted to give you the kind of a bird's view, and then tomorrow we're going to dig out the equations and look at the basics of density functional theory. And as I said, there is a course which is called FYS 1100, which actually spends the whole semester on applications of density functional theory. But that's applications where you actually run code, because this is a big industry. And the university uses a code which is called VASP, and the license is something like 100,000 Norwegian kroner per year. So that's a company which has developed that code. And it's widely used in material science. I know that some of you are using density functional theory in your thesis work.
Next one.
So this course runs during the fall. And it's a course which has been tailored to people from the material science. and it has a much more practical approach. So they would say something about Hartree-Fock theory, but they would not derive the equations like we have done. They set up the theorems, etc., for the Hohenberg-Kohn theorems, and they go through some of the formalism, but then everything is tailored to practical applications, and where you run the codes with different sets of materials and then try to extract a single particle basis which is relevant for that material. So it's a more practically tailored course for people in material science.